All right, so we've seen that we can make a data box that represents both a maximization and a minimization problem. Now, just parenthetically, I'm skipping section 5. Section 5 is about simplex method, which is about a practical method for solving maximum and minimum problems. Realistically, what you'll do is use a computer program to do the solution. The simplex method shows you how the computer does it, but it's not something that you would, in practice, use a lot. It's good to understand it, but I don't want to emphasize that in this first course. So, let's get back to this idea of dual problems. Now, is it just a mathematical game that you have two problems using the same data box? Or is there actually a meaning to the two different problems? And the answer is yes, there is a real practical meaning to the two different problems, that both problems can be useful in different circumstances. So let's go investigate that further. Now, you remember a couple videos back I had a long discussion about the dimensions of the quantities in the data box. And it turns out that when you have dual problems, the dimensions of the minimization variables are not the same as the dimension of the maximization variables. All right, so the dimensions are different. So these variables have different interpretations. So what are the dimensions of the maximization and minimization variables? Well, the dimensions of the maximization variable is the ratio of the dimension of bi, which is the constraint, divided by the dimension of aij for any I. We can go back and see that for our auto truck example. So here's the same data box we did before. Now, if you remember in the previous discussion, what I did was I derived these units here, and I also took the units of x, what x had to do, and then I figured out what the units would have to be in the data box here. Now, what really has to happen is the units here at this entry times the units here have to end up with the units here. So the units of a times the units of x have to be the units of b. So you have basically the equation ax equals b. That means that x equals b over a. So the units of the variable must be the same as the units of the constraint divided by the units of the coefficient. So that gives me my units of x. On the other hand, the v units, we have the same sort of thing, that in order to get the constraints going down to be consistent and have consistent units, the units of v times the units of a have to be equal to the units of c. So you get basically v times a equals c, or v equals c over a. So that's what we have here in this rule for determining dimensions of variables. All right. So I'm sure this is very confusing. Work through the examples, think about it, ponder it while you're waiting for the bus or whatever you do, or taking a shower, and try to internalize this idea. All right, so we have these two examples where we have that. So I think I can just skip over that. So let's go to this example here. Okay, well, this refers to the auto truck example that has this data box up here. So we have, if you remember this, that there's two shops, and each one can produce trucks and autos. And the maximization problem is to maximize profit, and the minimization problem is to minimize costs. The profit will be given by 300x1 plus 200x2. The cost will be given by 180v1 plus 135v2. All right. So I'm not going to actually do the solution, but you could graphically find the solutions. And the solution to the maximization problem is 3015. Solution to the minimization problem is 100 over 3 and 400 over 9. And it turns out that the two optimum values are equal to each other. Maximum value is equal to the minimum value. Now, what are the dimensions of this solution to the minimization problem? Well, go up here and see. It's going to be the dimensions of C divided by the dimensions of A. So the trucks cancel and I get dollars per man hour. So as the book remarks, this V sounds like a value per man hour. How much is each man hour worth? All right. So let's see how that works. If that's really the value of a man hour, then what you could do is increase the number of man hours from 180 to 183. Now V1 is the number of shop 1 man hours. So if you increase the number of shop 1 man hours from 180 to 183, and if you did solve the new problem, you would get a new solution and a new value for the objective function. Now notice the change in the objective function. The objective function has jumped up by 100. We've increased V1 by 3, and the objective function has increased by 100. In other words, we can make $100 more than before. Now what's the relation between increasing V1 by 3 and increasing the objective function by 100? Well, that's actually the value of the optimum solution V1, 0. If I multiply 3 by V1, 0, I will get 100. In other words, this 100 over 3 gives me the value of increasing the number of shop hours in shop 1 by 1. If I increase the number of shop hours in shop 1 by 3, I'll get 3 times the increase. If I increase the number of shop hours in V2 by 9, I would get an increase of 400 in the objective function value. So what does this 100 over 3 mean? Well, this is the minimum amount that the owner would pay a shop 1 worker in order to improve his net profit. I mean, he would have to pay the new person $33.33 an hour. And if he paid him $33.33 an hour, he would increase his profits by $33.33, so he'd just break even. So if he could get away with paying the new worker less than $33.33, then he would make more money by hiring more people in shop 1. Similarly with shop 2. If he could pay someone to work in shop 2 for less than 400 over 9, then he could make a net profit by hiring additional workers. All right. Now there's a caveat here, and the caveat is that this only works for small increases. If the increase is too big, then it's not going to work. And the reason is that as you change the problem around, the corner point may end up changing as you shift the boundaries around. If the corner point changes, then this doesn't work anymore. But as long as you're using the same corner in your optimum solution, this is going to happen. That if you increase the value of the constraint by a certain amount, meaning that you add more capacity, then the value of that additional capacity is given by the value of the dual variable. Now, I'm sure you didn't get that completely on this first hearing. Look at this again. It's worth thinking about this. This is a very important and really kind of cool relationship between two different problems. So what he's saying in this paragraph is pretty much what I said, that basically how much would you pay someone for overtime? Well, in this case, you wouldn't pay a shop worker in shop 1 more than $33 for overtime, or you'd be losing money. Okay, and the same thing for here. Now let's work for the other direction and start with the minimum problem and see what the dual problem means in that case. So this one is for the mining example, which we have the tableau. Well, the tableau is up here. And we want the units for the x variables. So in this case, the x variables have dollars per ton. And this is dollars per ton of the different types of ore. So let's see if we can apply the same reasoning that we applied over here. Remember that we said that the solution for V1 was such that if I increase this capacity by 1, then my profit would be increased by the value of V1. If I increase this capacity by 1, my profit would be increased by the value of V2. Right? So the same thing can be said here, that if I increase this requirement by 1, then the additional cost in the minimum cost problem will be given by the value of x1. If I increase the requirement for middle grade ore by 1, then the increase in cost in the best cost solution will be given by x2. If I increase this by 1, then the increase in cost will be given by x3. So we can call these marginal costs. Basically, it says change in requirement is going to bring what kind of change in the cost of the solution. Now, we have a rather strange situation here. In this optimum solution for the maximization problem, we have a 0 here. So according to what I just said, the cost of, it seems like the cost of producing an additional ton, let's see, an additional ton of low-grade ore is equal to 0. Yeah, this one is low-grade ore. Let's go up and see. Low-grade ore was the third column. LG stands for low-grade. So what it's saying down here seems to be that producing low-grade ore costs nothing. But that's not actually what it means. It means that if I raise the requirement for low-grade ore, that's not going to increase the costs anymore. Because in fact, in the optimum solution, you're already overproducing low-grade ore. Okay, so if you raise the requirement, that's not going to add any additional costs. And that's what he says down here. All right, in a way to summarize the two cases that we've looked at, maximum and minimum, we can try to do a general interpretation. In the maximization problem, x is the variable that you're solving for. So you could say x is an activity vector. That's what you're doing to increase profits. Okay, and b is the capacity constraint vector. You only have limited capacity of resources. C is the profit, and then what is the interpretation of the solution of v? Well, v is the imputed value vector. What that means is that if I increase the capacity, if I increase any one of these capacities, how much is my profit going to increase? So basically it gives, if I give 1 unit of increase in any entry of the vector b, then the increase in the profit is going to be the corresponding value in the vector v. Right? So it's basically the opportunity, it's called the opportunity cost of increasing your resources. Okay. On the other hand, if we have a minimization problem, then v is your activity. That's what you're doing, and the activities have a cost. And the c is the requirements vector. You have to meet certain requirements. So what happens when you raise these requirements? Where you're going to have more costs. So what's more costs going to be? If I raise any entry of this vector c by 1, then the increased cost of the best solution is going to be given by the corresponding value of the vector x. Now I think that you just have to do examples to understand this and really grasp it intuitively. And hopefully that gets you some idea of the relationship between v and x and the practical interpretations of these two vectors. Okay, so now we're going to put it all together and really tie the knot that relates to the maximum and minimum problem. All right, so we do have this maximum problem and minimum problem that we've seen before. Right, this is maximize, where you have this is going to be a less than or equal to constraint, so the y is positive. This is a greater than or equal to constraint, so the u is also positive, but we have minus u on the left-hand side. Yeah, here we're trying to maximize, here we're trying to minimize, and so on. All right. Now it turns out that when you have these two problems using the same matrix A and the same vector C, same vector B, in fact, the solution of the maximum is equal to the solution of the minimum. So that's what's stated down here, that the solution to these two equations actually give the very same value. Now, this result has some implications. If you remember the so-called Tucker's duality theorem back in section 4, let's jump back there for a second. So here it is. You can review the video for chapter 4 or read the chapter if you want to get back into this, understanding this. So here you have any feasible solution for the minimization problem minus any feasible solution for the maximization problem is going to be equal to this sum. This is vector v times vector y plus vector u times vector x. And the point I made in the other video was that v, y, u, x are all non-negative vectors. Every entry in v, every entry in y, every entry in u, entry in v, x is either positive or 0. So this is going to be true for any solution. The minimization problem, feasible solution for the minimum, feasible solution for the maximum. Now, if you find the very best solution for the minimum problem and the very best solution for the maximum problem, the duality theorem says that they're equal. So if g is equal to f, then this left-hand side is 0, so this right-hand side is 0. However, we know that every term over here is non-negative. It's either 0 or positive. Now, if the left-hand side is 0, that means every single term on the right-hand side must be 0. All the terms in here must be 0. Now, it looks like there are two terms here, but there's more than two terms, because v is a vector, y is a vector. Vy is v1y1 plus v2y2, etc. Ux is u1x1 plus u2x2, etc. So there are a lot of terms here that we have just shown are equal to 0. So let's go back and see what that means. All right, now here he's stating the result that I just said, that the optimum solutions are equal, so I have 0. So all of these terms must be 0. This must be 0, this must be 0. And every component of v0, y0 must be 0. Every component of u0, x0 must be 0. So that's what this is saying here. For each y, either v, for each I, for each component of the v is either the component of v is 0 or the corresponding component of y is 0. Now remember that these y's were these slack variables that we introduced in order to make equalities out of inequalities. So these y's don't really have a practical interpretation. But y is 0 when this constraint is satisfied exactly. Now there's actually a significance here. What does it mean that vi of 0 is equal to 0? Well, that means that if I increase bi by a certain value, then, or if I increase bi by 1, then the value of the solution of the maximum problem will also increase by 1. Or I'll increase by vi, sorry. Let me say that again. If I increase bi by 1, then my maximum solution will increase by vi. Okay? So this is saying that if an increase in bi produces an increase in the value of the maximum solution, then this constraint must be satisfied. In other words, you're only going to do better by increasing the resources if at the maximum solution that resource is fully utilized. If that resource is not fully utilized, then you can add more of the resource without increasing your profit, because you're not using the resources anyway. And what this one is saying is something similar. This one is saying that if you raise requirements, that's only going to increase your costs if at the optimum solution you're just barely meeting your requirements. If you're meeting your requirements and have some extra, then increasing the requirements is not going to change the cost of your solution, because you've got some extra left over in your optimum solution anyway. So this complementary slackness theorem really doesn't have a practical interpretation. And here's some examples that show it. And the rest of this is a more technical discussion of the simplex method, so I'm not going to go through that. So we'll stop here.